Hello, everyone. I'm Stephen McQuay. I am currently a Fusion IO employee, and I get to hack on Python during the day for my job, and I enjoy doing dabbling, I suppose, in computer graphics stuff at night. In fact, I would like to set this up as a disclaimer. Some of the stuff I may say might not be completely correct. Please feel free to correct me during the questions time. But it's stuff that I find really interesting. I've found it interesting for a few years now and just have kind of been picking it up here or there. Yeah, Fusion IO, my employer, was kind enough to send me here, so I'd like to mention them and thank them publicly. Yeah, and so a bit of history of how I've kind of come to be here today. During my education, I thought I would give Blender, which is an open source 3D modeling, texturing, lighting, animating application. I thought I would try to use that to do mechanical design, which it fails at, but I was able to learn about some of these more artistic mathematical constructs. And this is Blender running here on the screen. Eventually, I took a curves and surfaces class there at university, and that's kind of the sum total of my knowledge. Whatever I haven't learned about from Wikipedia, that's where I got it. And so, what I was kind of hoping to do today would be to give a background as what are subdivision surfaces, and kind of a more general education, and then kind of show you what's been implemented and kind of my vision for the future. So what you see here on the screen, I think, yeah, this is a simple face. Okay, a face is composed of edges and vertices. I just want to lay out some of the terminology. So each of these, vertex or point connected with another point, that would be an edge, and then a collection of edges would be a face. Another concept that's important in this realm is the idea of curve continuity or surface continuity. If 2 points meet, we call that C0. If 2 points have the same tangent, we call it C1, and so on with the derivatives. And generally speaking, what people look for, in computer graphics at least, is C2 continuity. If you've got C2 continuities, things look good, right? In fact, the way it was explained to me first was if you had if you're going to make a rendering of a hood on a car or something, you had vertical lights overhead, C2 continuity will guarantee that the lights, as they reflect off of that hood, they'll be nice and smooth. You won't see any sort of kinks in the lighting or anything. And so the idea with a lot of the tools and constructs that exist in a program like Maya or Blender is give the artists tools that they can use to create beautiful, C2 or what have you surfaces, and make them, as easy and as little friction to use as possible. So, let's see. As an example, here's a surface, that's pretty smooth, right? Fairly smooth. But the problem is the way I defined this one was just a collection of vertexes and edges and faces. I mean, there's no math behind this, right? Here are a bunch of points. They're connected this way. If you ask the artist to adjust this, right, they can move a vertex at a time, and that would be slow. And there are other ways to do this, right? You can say, well, let's draw a circle and kind of do some sort of scaling in that circle and move things around. But that would also yield inconsistencies. In certain places you wouldn't be guaranteed that curvature. So there's another. Well, there's a mathematical tool. So I'll make sure this is lined up. Who here has heard of Bezier curves? Okay. Maybe I shouldn't be going so slow then, sorry. But Bezier curves, basically what Bezier curves allow you to do is accomplish what I was saying, right? You can, I'm still doing this proportional mode stuff. I'm moving at most 4 points here and controlling a very smooth surface, right? And this, so what's so cool about that? Well, sorry, that is exactly what's cool about that, right? You control 4 points and you've got this beautiful, smooth surface. Now, what happens if this is not sufficient to describe the geometry that you, the artist, want, right? Like, oh, well, I want this to undulate more than just the 2 times. Well, you got a couple of options, and each option has a pro or a con. Like, you could increase the degree of the curve, right? This is a degree 3 curve. You could increase the degree of the curve, which adds, computational complexities and what have you. And it's fine, you can do that, but, the mathematicians of the world have come up with clever ways to, minimize computational power or computational requirements while still giving the artists, these guaranteed curvature properties. So this, for example, is a NURB curve, non-uniform rational B-spline, I think is the full expansion. And basically, all NURBs are mathematical tools that you use that basically constrain a string of lower order Bezier curves. And between each of those Bezier curves, you're guaranteed to maintain continuity. Does that make sense? So like I said, just a tool. It's just a tool. I can move this around here. The underlying mathematics basically guarantee that between any of those sub-Bezier, those normal Bezier curve subsections, that continuity is maintained, right? So that's pretty cool. Because it not only allows for simpler, it minimizes the CPU requirements, right? The long-term CPU requirements, and still gives the artist, tools that he or she can do her job. And this generalizes. There we go. This generalizes into 3D as well. So we're back to that weird, sombrero-shaped surface, but now I have a finite collection of points, and I can move this surface around, and you're guaranteed curvature across that patch, that Bezier patch. Which is cool, but that's not why we're here. We're here to talk about subdivision surface schemes, right? And so what limitations exist with this technology, and why would you want something different, right? And the way I understand it, and I'm sure the mathematicians in the room will correct me afterward, but the way I understand it is when you go to create organic models using NURB surfaces, it can be difficult to create a topology such that you maintain curvature across all the different faces. And that happens when, for example, you try and model, I don't know, like a human face or a twig or something, and you can't model that completely using these Bezier patches, these rectangular Bezier patches. And so you have to use like triangles and what have you. And as I understand it, curvature, it's significantly more difficult to maintain those curvature properties. So people came up with an alternative technology, notably Ed Catmull, who is, does anybody know who Ed Catmull is? Great. Ed Catmull is he started Pixar Animation Studios. He's kind of the brain behind a lot of the math and such that they use to create all those videos that my kids love. I thought it might be easier to demonstrate the Catmull-Clark subdivision scheme by demonstration. Then I'll go and show you a little bit of, or at least, show you a few of the mathematical constructs, and then point you in directions of where you could learn more if it interests you. So essentially, what happens here is for each face in a given mesh, you add a new point for that face. And for each edge in a given mesh, you add a new point for that edge. And then each existing vertex gets a new vertex in the next subdivision. So it's a recursive smoothing algorithm. Okay, so I'm gonna run it really quick. For one subdivision on this cube, I want you to pick a face and watch that face get a new one and the edge and so forth. So I don't want to quit Blender. There we go. Okay, so the face gets a new point, and an edge gets a new point, and then the vertex gets a new point. and so on and so forth. You notice if you keep doing that, it's pretty smooth. In fact, it's, I can't recall which one this is. I believe it's C2 continuous everywhere but at what they call extraordinary vertices, which I'll explain in a second. But regardless, it's very, very smooth, and furthermore, it generalizes a bit more nicely than the Bezier patch method for creating models, right? So, yeah, let me just pull up really quick the maths here. So basically what happens is for each, what you basically do is you take the 4 points for a face and you just average them, right, in space, new point. And then for each edge, you take these 2 points and you average them normally, and then you average these guys by, I think, a factor of half, and that yields this point here. And then you do something similar for each point. They are influenced by each of their neighbors, recursively, and so on and so forth, and then you get a nice smooth surface. Issues do arise when vertices have a valence that is not 4. Yes?
How many iterations did it take to get between your square?
That's a good question. I'll come back around to that in just a second, because there are very interesting performance characteristics with this method. But valence is basically how many edges come out of a given vertex. So the vertex over which my mouse is has valence 4, right? If it doesn't have valence 4, then there are issues. And I think I've got this thing queued up for, yeah, okay. So this might be hard to see. Focus like right in this region as I rotate the model, and you'll see there's kind of a sharpness there, i.e. the continuity is not maintained at that point. Maybe it's harder to see. And this is a fairly simple model. It's much more apparent when you have a model that's more complex. But let's go ahead and investigate this and see what's happening. You'll see that the underlying mesh, this vertex right here, has valence not 4. And therefore, the scheme does not give you any sort of continuity guarantees. Anyhow, so that is, this stuff all has existed in Blender, for the longest time, and you may be wondering, well, why are you here? This stuff's already done, and I'll get to that. But first, yeah, let me remember to get back to the question from earlier. And anyhow, here we are. So that was, oh, come on. So I'm gonna run the subdivision again, right? So this is the first step, second step, third step, fourth step, fifth step. And basically at the fifth step, you'll note that, at least for my eyes and the monitor that's way back there, oh, I guess over here you can still see some edges, but it's fairly smooth, right? If you had been watching up here on the vertex count, face count, and then generally the memory consumed, it scales poorly because, as I had the slide up before, each face gets a new vertex, and each edge gets new vertices, and the vertices from before are copied over. It scales poorly, to say the least. Fortunately, though, if you run a few iterations of this and then do like just your typical normal base smoothing, right? It looks great. It looks great for rendering a still image or making a movie or what have you. I guess one of the things one of the terms I wanted to introduce was this idea of a stencil. But I guess it's better served here in a second. So, okay, this is worth noting. I want you to look at the original mesh and then look at the surface that was generated with this, and note that the final surface does not interpolate the original points. Right? So if you were to, for example, scan points in on some surface that you cared about, read that in as an STL or what have you into Blender, and then run the subdivision scheme, the surface smoothing scheme, it would pull away from the points. Right? There are no guarantees whatsoever about your original points, which, for most artistic purposes, is great and fine, no problem. But that coupled with, while this method has looser topology requirements than like using just Bezier or NURBS patches, there still are those issues like I showed you. Valence not 4 gives you these discontinuities. So there is an alternative subdivision method called 4 minutes. Okay, butterfly subdivision surfaces. And I swear I had this here. Here we are. Where essentially, now it does suffer, I shouldn't say that it doesn't suffer from valence issues, but essentially you can have a purely triangular mesh, and as long as it has good valence at all of the vertices, basically what you do is, this subdivision scheme is fairly easy. The black points here indicate your original mesh, and the red point here is the new vertex you're trying to add. For each edge, add a new one using this stencil. The stencil means, well, which of all of the original vertices are you going to use to generate this new one? And you'll notice that it's a compact stencil, which means that I don't need to know something about the entire mesh in order to calculate a new vertex, which is nice. And basically all you do is, well, this one contributes half of its location, an eighth of this location, minus 16, so on and so forth. And this method yields C1 continuity across the board, except for under certain valence conditions. Somebody, Zoran, I believe, improved on this method, and basically what I've done so far is I've implemented Catmull-Clark, which works fairly well in Blender. I've implemented the original butterfly scheme, which has some limitations, and I'm to the point now where I'm going to implement some of these alternative butterfly schemes, which add more and more coolness to the butterfly subdivision scheme, which will eventually yield an interpolating subdivision scheme. The reason I did this was because Blender lacks this feature, and I wanted to kind of play with it in Python before trying to jump into the C++ code and implementing it there. I'm sure there are you in the room who are much more knowledgeable about this or Python in general or what have you than I am, and I would really appreciate contributions. You can look me up, smcquay, SMCQUAY, on GitHub, or steven@mcquay.me. So, thanks. 2 minutes. So I have 2 minutes for questions.
Do you have any demos
Of it working? Yeah, I've got a demo. Let's see. So this might not be super hyper exciting. Unfortunately, the demo I want to have is a button in Blender that does the scheme for you. But all I got right now is iterate, and then you can give it like which scheme you want. So Catmull-Clark, give it the mesh, Blender, samples, cube, and that basically contains vertex information, edge information, connectivity, and what have you. And then you say how many iterations you want to do, right? So you can see you crank that up to 5, and it's a lot more information. And this one actually works just fine for, let's see, which one? Simple tet, for example. Oh, actually that works for Catmull-Clark as well, but if you were to, what I meant to do was butterfly, you'll see that it generates eventually all the information for that. So it's functioning, and I've got little buttons in Blender so you can visualize it and all, but it's still a work in progress. I'd hope to tune some stuff in Python, at this point, and I ran my first profile yesterday. It was interesting to see what was slow. My midpoint calculation was what's slowing things up. Anyhow, any other questions? Okay, thanks. Oh, sorry, over there.
resources for learning Python in Blender.
Mm-hmm.
Would you recommend anything there? Because I know Blender's got a really cool Python interface. Blender's really complicated.
Yeah, and their API is kind of this moving target, right? I did a presentation at the local user group back in Utah this year, and it's a moving target, and it is cool. You can do really cool things about it. The resource I would recommend you go and look at is their documentation wiki. Yeah, that's what I would point you at. So, thanks everyone.